In this presentation, I'll go through some notes from Chapter 7 of book Designing Data-Intensive Applications. Chapter 7 is called Transactions. So here is a beautiful diagram from the Chapter 7. Here, as you can see, from top to bottom, no phantoms, serializable, snapshot isolation, MVCC, read committed. We are going to talk about all these things. So transactions are an abstraction layer that allows an application to pretend that certain concurrency problems and certain kinds of hardware and software faults don't exist. A large class of errors is reduced down to a simple transaction abort, and the application just needs to try again. Without transactions, various error scenarios like process crashing, network interruptions, power outages, disk full, unexpected concurrency, etc. mean that data can become inconsistent in various ways. For example, denormalized data can easily go out of sync with the source data. Without transactions, it becomes very difficult to reason about the effect that complex interacting accesses can have on the database. This chapter went particularly deep into the topic of concurrency control. We discussed several widely used isolation levels, in particular read committed, snapshot isolation, sometimes called repeatable read, and serializable. We characterized those isolation levels by discussing various examples of race conditions, like dirty reads. One client reads another client's writes before they have been committed. The read committed isolation level, stronger levels prevent dirty reads. Dirty writes, one client overwrites data from another client that has written but not yet committed. Almost all transactions implementations, they prevent dirty reads. Read skew, that is non-repeatable reads. A client sees different parts of the database at different points in time. This issue is most commonly prevented with snapshot isolation, which allows a transaction to read from a consistent snapshot at one point in time. It is usually implemented with multi-version concurrency control. Lost updates. Two clients concurrently perform a read, modify, write cycle, one overwriting the others. One overwrites the other's write without incorporating its changes, so data is lost. Some implementations of snapshot isolation prevent this anomaly automatically, while others require a manual log, that is select for update. Write skew. A transaction reads something, makes a decision based on the value it saw, writes the decision to the database. However, by the time the write is made, the premise of the decision is no longer true. Only serializable isolation prevents this anomaly. Phantom reads. A transaction reads objects that match some search conditions. Another client makes a write that affects the results of that search. Snapshot isolation prevents straightforward phantom reads, but phantoms in the context of write skew require special treatment, such as index range locks. Weak isolation levels protect against some of those anomalies, but leave you, the application developer, to handle others manually, by using explicit locking. Only serializable isolation protects against all of these issues. We discussed 3 different approaches to implementing serializable transactions. The first is literally executing transactions in a serial order. If you can make each transaction very fast to execute and transaction throughput is low enough to process on a single CPU core, this is a simple and effective option. Second is two-phase locking. For decades, this has been the standard way of implementing serializability, but many applications avoid using it because of its performance characteristics. The third is serializable snapshot isolation, or SSI in short, a fairly new algorithm that avoids most of the downsides of previous approaches. It uses an optimistic approach, allowing transactions to proceed without blocking. When a transaction wants to commit, it is checked and it is aborted if the execution was not serializable. Here are the topics discussed in this chapter. The slippery concept of a transaction. And then in this topic, we discussed the meaning of ACID, single object and multi-object operations. The second is weak isolation levels. And here we discussed read committed, snapshot isolation or repeatable read, preventing lost updates, write skew and phantoms. And then serializability. Here we discuss actual serial execution, two-phase locking, and serializable snapshot isolation, or SSI in short. What is meaning of ACID? The safety guarantees provided by transactions are often described by the well-known acronym ACID, which stands for atomicity, consistency, isolation, and durability. Systems that do not meet the ACID criteria are sometimes called BASE, which stands for basically available, soft state, and eventually consistent. Meaning of ACID. So atomicity. In general, atomic refers to something that cannot be broken down into smaller parts. The word means similar but subtly different things in different branches of computing. Consistency. The idea of ACID consistency is that you have certain statements about your data that is invariant, that must always be true. For example, in an accounting system, credits and debits across all accounts must always be balanced. Isolation, in the sense of asset means that concurrently executed transactions are isolated from each other. They cannot step on each other's toe. The classic database textbooks formalize isolation as serializability, which means that each transaction can pretend that it is the only transaction running on the entire database. The database ensures that when the transactions have committed, the result is the same as if they had run serially, even though in reality they may have run concurrently. Durability is the promise that once a transaction has committed successfully, any data it has written will not be forgotten, even if there was a hardware failure or the database crashes. Weak isolation levels. Let's talk about read committed. The most basic level of transaction isolation is read committed. It makes two guarantees. When reading from database, you will only see data that has been committed, that is, no dirty reads. Second, when writing to the database, you will only overwrite data that has been committed, that is, no dirty writes. So basically, read committed ensures no dirty reads and no dirty writes. Snapshot isolation and repeatable reads. The idea is that each transaction reads from a consistent snapshot of the database. That is, the transaction sees all the data that has committed in the database at the start of the transaction. Even if the data is subsequently changed by another transaction, each transaction sees only the old data from that particular point in time. Snapshot isolation is useful isolation, especially for read-only transactions. However, many databases that implement it call it by different names. In Oracle, it's called serializable, and in PostgreSQL and MySQL, it's called repeatable read. Snapshot isolation is a popular feature. It is supported by PostgreSQL, MySQL with the InnoDB storage engine, Oracle, SQL Server, and others. Preventing lost updates. The lost update problem can occur if an application reads some value from the database, modifies it, and writes back the modified value. That is a read, modify, write cycle. If two transactions do this concurrently, one of the modifications can be lost because the second write does not include the first modification. We sometimes say the latter write clobbers the earlier write. Write skew and phantoms. You can think of write skew as a generalization of the lost update problem. Write skew can occur if two transactions read the same objects and then update some of those objects. In special case where different transactions update the same object, you get a dirty write or lost update anomaly, depending on the timing. The effect where a write in one transaction changes the result of a search query in another transaction is called a phantom. Snapshot isolation avoids phantoms in read-only queries. But in read-write transactions like the examples we have discussed in the book, phantoms can lead to particularly tricky cases of write skew. Serializability. Serializable isolation is usually regarded as the strongest isolation level. It guarantees that even though transactions may execute in parallel, the end result is the same as if they had executed one at a time, that is, serially without any concurrency. Thus, the database guarantees that if transactions behave correctly when run individually, they continue to behave correctly when run concurrently. In other words, the database prevents all possible race conditions. Summary of serial execution. Every transaction must be small and fast because it takes only one slow transaction to stall all the transaction processing. It is limited to use cases where the active dataset can fit in memory. Rarely accessed data could potentially be moved to disk. But if it needed to be accessed in a single threaded transaction, the system would get very slow. Write throughput must be low enough and can be handled on a single CPU core, or else transactions need to be partitioned without requiring cross-partition coordination. Cross-partition transactions are possible, but if there is a hard limit to the extent to which they can be used. Two-phase locking. For around 30 years, there was only one widely used algorithm for serializability in databases, that is two-phase locking. We saw previously that locks are often used to prevent dirty writes. If two transactions concurrently try to write to the same object, the lock ensures that the second writer must wait until the first one has finished its transactions or aborted or committed before it may continue. Two-phase locking is similar but makes the lock requirements much stronger. Several transactions are allowed to concurrently read the same object as long as nobody is writing it, but as soon as anyone wants to write, that is, modify or delete an object, exclusive access is required. If a transaction A has read an object and transaction B wants to write to that object, B must wait until A commits or aborts before it can continue. If transaction A has written an object and transaction B wants to read that object, B must wait until A commits or aborts before it can continue. Performance of two-phase locking. The big downside of two-phase locking and the reason why it can't be used by everybody since the 1970s is performance. Transaction throughput and response time of queries are significantly worse under two-phase locking than under weak isolation. This is partly due to the overhead of acquiring and releasing all those locks, but more importantly due to the reduced concurrency. By design, if two concurrent transactions try to do anything that may be in any way result in a race condition, one has to wait for the other to complete. Serializable snapshot isolation, or SSI in short. SSI is very promising. It provides full serializability but has only one small performance penalty compared to the snapshot isolation. SSI is fairly new. It was first described in 2008 and is the subject of Michael Kyle's PhD thesis. Pessimistic versus optimistic concurrency control. Two-phase locking is so-called pessimistic concurrency control because it is based on the principle that if anything might possibly go wrong, it's better to wait until the situation is safe again before doing anything. It is like mutual exclusion, which is used to protect data structures in multi-threaded programming. By contrast, serializable snapshot isolation is an optimistic concurrency control technique. Optimistic in this context means that instead of blocking, if something potentially dangerous happens, transactions continue anyway in the hope that everything will turn out to be all right. This concludes Chapter 7 notes. Hope this was useful. Have a nice time. Like and subscribe for more such content.